Good afternoon. My name is Myung-ji Han. Thank you very much for having me here today. Let me start my presentation. Knowledge discovery on unstructured data from pattern matching to deep learning. This is the outline. I briefly talk about my background and present my research statement. And finally, I'm going to talk a little bit about my research and education plan. My background. I did my bachelor's degree and PhD in computer science and engineering at Seoul National University. After graduation, I've been working as staff engineer in mobile communication division of Samsung Electronics since 2018. Within this, I'm developing the speech recognition engine of Bixby, Samsung Voice Assistant. Plus, I'm serving as in-company instructor of AI and team change agent, a person who's in charge of the organizational culture of the team of about 300 people. I'm interested in combinatorial algorithms, pattern search, and data mining. Also, I'm especially into graph analysis and machine learning, such as automatic speech recognition, natural language processing, and graph neural networks. I think I'm quite fluent in C++, Java, and Python. I'm able to implement machine learning in TensorFlow or PyTorch. I feel comfortable with developing and managing a machine learning pipeline using Docker and Kubeflow. This is my selected publications. In my graduate school, my main research was about pattern matching on various data structures. In the company, I've mostly been studying speech recognition. Let me introduce my work on subgraph matching. Given a query graph and a data graph, an embedding is a mapping of vertices from the query graph to the data graph, satisfying that it's injective. The mapping pairs have same labels, and every edges in the query graph also exist in the data graph. Subgraph matching is the problem of finding all distinct embeddings, which is NP-hard. In this example, we have two embeddings. Applications of this problem include social network analysis, RDF query processing, chemical compound search, protein-protein interaction analysis, and etc. etc. Backtracking is the general framework that all existing algorithms are based on. That is, we find for every query vertex a candidate set which consists of data vertices that the query vertex can possibly be mapped. A naive way would be to choose every data vertices of the same label. Next, we choose a matching order of the query vertices, and according to that order, we map next query vertex recursively to its candidate set, as represented by the search tree on the top right corner. We aim to minimize the search tree, and it totally depends on a candidate set and a matching order. There are two SORA algorithms, TurboISO and CFL-match. They use a spanning tree of the query graph for filtering the candidate set. Specifically, we are checking possible matches of all the paths in the tree, while keeping only the vertices that could possibly map any path. For instance, V12 is filtered out since it can never map the path U1, U2, U4. We store the surviving vertices in an auxiliary data structure as shown on the bottom right corner. Next, we search the auxiliary data structure for the query graph. We are following an infrequent path first order, that is, we prioritize paths with less possible matches. For instance, path U1, U2, U4 has 3 possible matches, and path U1, U3 has 4 possible matches. So we select the matching order U1, U2, U4, and then U3. What's left is simple. According to the order we just decided, following the 3 paths, we are mapping data vertices one by one. While doing that, we are checking if every non-tree edges in the query graph are matched in the data graph as well. For instance, if we select V1, V4, V10, and V5 as in this picture, since all the non-tree edges are matched, we got an embedding. On the other hand, if we select V6, since the non-tree edge U2, U3 is not matched, we failed and backtrack. The first challenge of previous algorithms comes from the use of spanning trees. Since a spanning tree is a tree, we just forget about non-tree edges while we are filtering the candidate vertices. And this may cause a lot of false positives. Let's take a look at V9 in CU3. If we look back the data graph, it turns out that V9 has no edge to any single vertices in CU2. If we can remove V9 in the filtering phase, we don't have to traverse this unnecessary search tree. To deal with this, we come up with dynamic programming with respect to directed acyclic graph. In detail, given the query and data graphs, we first build an auxiliary data structure that looks like this. It has the same structure with the query graph, where in the place of each query vertex, we have the candidate sets. Also, in the place of each query edges, we have edges between every pair of candidate vertices, if and only if they have edges in the data graph. Now, following the DAG in a topological order, we filter out any vertices that doesn't have edges they have to have. For instance, we remove V9 since it has no edges to CU2. We are repeating this, alternating the direction of DAG until there's no more vertex to remove. The time complexity of each round is polynomial to the number of edges. The second challenge is about suboptimal matching order. As mentioned, previous algorithms adopt infrequent pass first strategy, and it may cause a redundant Cartesian products. Here we have a data graph, query graph, and its spanning tree. Since we have 10 possible matches for the red path and 100 possible matches for the blue path, we are matching the red path first. The search tree will become as big as 10 times 100. It's non-optimal. An optimal matching order will be U1, U2, U3. We don't need to traverse all 10 candidate vertices of U4 because if we check U3 early, we'll realize that it can never make an embedding because the non-tree edge is not matched. From this observation, we pointed out that non-tree edges should be checked as soon as possible. To deal with this, we come up with a DAG ordering that selects an order of DAG. For example, now we select U1, U2, U3, U4, U5, or likewise U5, U4. Another issue is about the static matching order. They decide the matching order in pre-processing phase and follow that fixed matching order throughout the whole search. However, the optimal matching order differs across different partial embedding. For example, if we map U1, U2 to V1, V4, and then U3 to V3, then it's better to choose U5 next. On the other hand, if we map U3 to V5, it's better to choose U4 next. From this finding, we come up with the adaptive matching order that selects matching order on the fly based on the current partial embedding. Specifically, we are selecting infrequent pass first constrained by DAG ordering. The final challenge is the redundant computations. Let's look at this example. It's the same query graph as the previous slide, except that they now have one additional vertex U6. Likewise, the data graph is the same, but it has 5 candidates for U6. Any reasonable matching order will map U6 following U1, and then try to map the rest of the query graph, which ends up with complete failures. In this situation, all the previous algorithms are trying to map U6 to other candidates, although it all will fail either. Why? Who caused all the failures below V167? At the bottom here, it failed because we couldn't map U5, and here we couldn't map U4. It's due to the mapping of U5's ancestors and U4's ancestors. After witnessing all the failures at the bottom, coming all the way back to U6, we now know that U6 is innocent for all the failures below, because U6 doesn't belong to the set of vertices that caused all the failures. We named this a failing set and devised a simple way to compute it while exploring the search tree. We compared our algorithm to all the previous algorithms with 6 different real-world datasets, and our algorithm outperformed all the others by orders of magnitude. We tested a big Twitter graph as well. The gap became much more significant, which proved the scalability of our algorithm. Now, before I move on to the speech recognition part, I'd like to briefly explain the basics of deep learning. Let's suppose we're given some labeled images of cats and dogs. An image is encoded as a vector of numbers, and a label is encoded as one hotback vector. With a bunch of this data, we'd like to train a neural model so that it can classify a new image into cat or dog. One simple way to do this is to use a threefold neural network. Given the input x, we perform a dot product of a weight matrix and the input, and we add a bias. Next, we apply a sigmoid activation function to get a hidden vector h. Deep neural network has multiple such layers, and at the final layer, we perform softmax instead of sigmoid, which converts the output to a probability distribution. Now that we have the model's output, a probability distribution of cats or dogs, we compute a loss by the cross entropy between the output probability distribution and the ground truth, which is one hot vector. Finally, we calculate the gradient of the loss and propagate it back through the network, and we're updating all the weights and biases to the opposite direction to minimize the loss. So this covers how we train the neural network as well as we do inference. What is end-to-end Esser? It is a system which directly maps a sequence of input acoustic features into a sequence of graphemes or words. The word end-to-end means we need just one single model as opposed to the conventional model approaches which train each of these sub-modules to optimize different criteria. This diagram represents the E3sr pipeline. Given an acoustic signal, we first extract feature vectors every 10 milliseconds, which is called a frame. The goal of audio encoding is to transform a sequence of hidden feature vectors into a sequence of hidden vectors. Here, t prime can be smaller than t if the model has some kind of time reduction technique, which normally is the case. But in this presentation, I'll assume that they are the same to make it simple. The goal of decoding is to transform the sequence of hidden vectors into a sequence of labels, or to be more precise, logits, where a logit is a vector containing the probabilities of each labels. Here, the large t and the small t should be different because the time scales are different between input and output. In particular, Large T is likely to be much smaller than small t, since large T is the number of labels such as graphemes or words, whereas small t is the number of frames that are produced every 10 milliseconds. Now that we have a sequence of logits of length t, where a logit has multiple labels as many as the English alphabets at the least. In this case, how many sentences can we make? As the large T gets bigger, the number of possible sentences grows exponentially. This is where the beam search comes in. The beam search optimizes the sentence by pruning out unpromising sentences during the search. As a result, we end up with a finite set of candidate sentences as well as their probabilities called hypotheses. Oftentimes, the word decoding embraces the beam search because they are always be performed in parallel. This presentation will mainly focus on the red box, namely audio encoding and decoding. LSTM is widely used for audio encoding, which is a type of recursive neural network. LSTM has a loop which allows the information to persist in the network, and this makes LSTM be capable of encoding a sequence. We usually unroll the loop since it makes it more intuitive, like this figure. We can input the sequence X from 1 to T, and if we do this, the LSTM unit will implicitly memorize the history and encode XT considering its meaning in the context. Bidirectional Lstm has two LSTM units, which allows the information to flow in both directions, which in turn allows for higher encoding quality. However, since it needs all the time steps to encode even H1, it only operates in batch fashion, and so we need all the input sequence as a whole for encoding. Let's simplify the diagram. The figure on the right shows an audio encoder by deep bidirectional LSTM. Again, the objective of decoding is to transform the hidden vector sequence into a sequence of labels. Connectionist temporal classification, or CTC, is the first E3sr model proposed in 2006. The structure of CTC is very simple. The encoder hidden vectors go to a linear and softmax layer, which produces a label at each time frame. How do we then change these long labels to a normal sentence? For this purpose, CTC introduces a special blank symbol, and we define a function beta that maps any arbitrarily long sequence into a short sequence that makes sense. A drawback of CTC is the label prediction at each time frame is conditionally independent from the previous predictions, which is the main reason that lowers the accuracy of CTC. That being said, a benefit of CTC is that at each time frame, we either output a label or a blank symbol, that is to say, it's streaming. Listen attendance pair, or LAS, is admittedly the first E3 model that has shown comparable performance with conventional models. It's also known as attention-based encoder-decoder model. It's autoregressive, meaning that the prediction of the current label is conditioned on the previous predictions. If you look at the figure, LSTM takes the previous label as input and autoregressively predicts the next label. Another input to the decoder is the output of the attention module, which looks at the encoder outputs and calculate which frames are relevant to the current predictions to finally give the decoder something called context vector. As you can see in the figure, the encoder and decoder run separately. In particular, The decoder starts after encoder finishes processing the whole frames. We need a special end of sequence symbol to let it know the end of decoding. Also, this encoder-decoder structure makes it hard to be streaming because it looks at the entire frames before making predictions. A recurrent neural network transducer is arguably the best streaming E3sr model. RNNT has audio encoder and label encoder. Without label encoder, it's just a CTC model. The label encoder encodes the so far predicted labels. We then have a joint network which combines label encodings and audio encodings, and this goes to a softmax which outputs labels or blanks. Reminding that the drawback of CTC was that the label prediction was conditionally independent across different frames. RNNT has addressed this issue by introducing the label encoder. Although RNNT is the best streaming model, its accuracy is still worse than LAS, since LAS looks at the full context by utilizing attention. We want a model to support streaming, but at the same time, we want a perfect final recognition quality. Two-pass ASR model combines the streaming RNNT and the full context LAS together. On the left side, we have a normal RNNT. On the right side, we have additional encoder that takes the audio encodings of RNNT. The last decoder calculates attention from this additional encoder. Now, RNNT is streaming the result, and then at the end of utterance, the last decoder operates to predict the hypothesis of the best quality. Though it is confidential, this two-pass model is actually running on Galaxy. For long, deep learning research has focused on Euclidean structured data such as text, acoustic signal, and images. By the way, this is why I think AI has a long way to go. Graph has strong expressive power of real-world data, such as social network, biological networks, YouTube clicks, digital transmission, etc. Graph neural network is a hot research topic. GNN, in particular, is designed to perform inference for various graph-related problems. It has a lot in common with combinatorial graph algorithms that I studied, and there are uncountably many potential applications like recommender systems, question answering, computer vision, physics, chemistry, drug discovery, etc. In ICLR 2021, a top-tier AI conference, I looked up all the papers that has award graph, and I found 167 rejected papers and 46 accepted papers. It's 20%. 20% of submissions are accepted. I think this number shows that this domain is so promising. I googled the keywords subgraph isomorphism and graph neural networks, and I found a number of recent cross-domain studies with notable results. In my humble opinion, I could make quite a big contribution to this area if I get a chance. I have preference to algorithms, data structure, and theory of computations as basic courses. As advanced courses, I'd like to teach big data analysis and machine learning. As a practical course, I'd like to teach on-device speech recognition, where students will implement speech recognition apps running on Android. My teaching methodology, I prefer to provide small examples covering all cases. All the examples in this presentation, I drew all of them myself. 1,000 words are not worth one good figure. I really think a lot to make such figures that is as small as possible, but at the same time not missing any important notions. Also, I give drawing as assignments because I think once you draw, you'll never forget. What I've studied in my early days of graduate school, string matching for instance, is developing so slow. All the great theories have already been found. That being said, I still think it's important to study them because there's no better way to develop one's thinking power. AI, by the way, is changing so rapidly. All of that history of ASR I presented today happened in only the last couple years. All the 수상님s in my team who majored in speech recognition, sadly, have little knowledge of the recent technologies. That's why I pursue where theory meets practice. We have to keep our balance. We should train ourselves, applying what we learn into practice quickly. I do my best to do this if I get a chance. This is the end of my presentation. Thank you so much.